Onward juries and value competitors can I'm Chen from Jingshan High School, and today I'll be the reporter for problem 8, irregular potential lines. So here's the problem statement. Place two electrodes into water, supply the state voltage, and use a voltmeter to determine electric potential at various locations. I'm going to investigate how the measure with the equal potential lines deviate from our expectation for different conditions and liquids. So the main focus for this problem is what is the reason for the equal potential line deviation and how different parameters will affect the equal potential lines. So here's our outline. I'll start with the observation, the theory, experimentation, and last but not least, the conclusion. So here is the observation video. We use one probe of the multimeter to test different spots of our plane, which has electrodes inside, and we map the same electric potential at our graph paper, and we line where there is the same electric potential, and we get the electric potential lines, equal potential lines. And here are some available parameters that we'll investigate in this experiment. So firstly is the different concentration of liquid, and second is strong and weak electrolyte, and the third is the settling time. For any equal potential lines, we measure by multimeter and map onto our graph paper, and we expect it will be symmetric, and I will explain this further. And we think that the deviation is caused by the triangling of items and the time spent when we test the graphs. Here's our theory part. So I'll talk about the electric potential. So first we consider the positive point charge that moves from point A to point B. And so the work done is transferred into electric potential energy. And due to the definition of a potential difference, we could get this formula. And since the dot product of the dot AB and dot AC is the same, so they have the same potential difference. So if we line these two dots, we can get the equal potential line, which is the problem statement plus due. So some characteristic is the same charges on there will have the same electric potential energy, and it is also known that there will be perpendicular to electric lines. Then I'll move on to double layer theory. The double layer theory states that the areal charge density will be proportional to the root of the initial ionic concentration. So the further it is from the electrode, the electric potential will drop with the distance. So this could be used to explain the tensor at electrode, which I will show you in my experiment results. Now I'll talk about the Fick's law. The first Fick's law says that the diffusion flux is proportional to the changing of the concentration of the liquid with respect to the distance. So the diffusion flux here, we could see it as the equal potential line, the density of the equal potential lines. And I'll move on to the second Fick's law. The second Fick's law states that the change of the time will cause the concentration to also to spread out, and will cause the concentration gradient. So so this is the Fick's second law. Here we try to plot out the potential distribution. So here, first it is the line. So we consider 2 points over here, and if this is measured dot, the dot of the electric potential, so it has a x to one electrode, and e minus x to another electrode. So if we add to electric potential, we get this formula. And then we consider a plane. So the measured dot is over here, and it is R1 from one electrode, and R2 from another electrode. So again, we add to electric potential, and we could get the final formula. Then, if we plot these two formulas that we get from our derivation, so we can see how the voltage will related to the distance. And this is a graph from a line between the two electrodes, and this is the surface. And you can see that if we're closer to the electrode, the higher the voltage will change. And we see the plane. This is a symmetric distribution that I've said in the introduction, and this would be our expectation. And also we use water as our expectation because we think that the deviation of the equipotential line is due to the dissociation of the electrolyte. So the water will be like there are no dissociation. There will be little dissociation. So we could see that this as our expectation, like a symmetric distribution of the equipotential lines. And this is our theory, symmetric distribution. And here I will move on to my experimentation. So here is the experiment setup. Here we connect one part of the power supplier to one probe of our digital multimeter, and the other to one electrode. And we can use another probe of our multimeter to measure different dots on the board. And the plastic board here has different electrolytes or water, and we could measure it on our graph paper, and we will map it to Excel and GeoGebra to analyze. And it is important to point out that our electrode we use carbon rod, so it will not dissociate. It will only dissociate like water, and we use a thermometer to make sure that the temperature is controlled. So first thing we want to know how the water depth will affect the experiment result. So here is our theoretical line, and we change the different depth of our multimeter probe, and we can see that from 0.4 centimeters to 1.4 centimeters, it will always have the same trend with the theoretical line, and it has a great fit. So we think that the water depth will not affect the equipotential line distribution. So now move on to our first experiment, which is a different concentration of our electrolyte liquid. So we use copper sulfate for our experimentation, and we do different three kinds of concentration, 1N and 0.1N and 0.01N. And we would expect that it will be denser at the electrode because of the double layer theory. So this is the result I got from 0.01 experiment, and it has a voltage variation of 1 volt. And so here the different colors is correlated to one voltage, and this is our equipotential line distribution. So here's a result for 0.1 concentration. It has a voltage variation of 1.5 volts. And here is the concentration of 1M, and it has a voltage variation of 1.6 volts. So we can see here, because we measure our dots from the left to right, and we could see that the gradient will decrease with time. What I mean is, here is denser and here is less dense. And we could explain this using the fixed second law. And we could also observe that the gradient here is higher at the electrode. And this is partly because of the distribution of the electric lines, and it is also correlated to the double layer theory. And here's a discussion. So we can see that the concentration goes higher, the voltage variation also becomes bigger. So we could explain this using the fixed first law, which is the changing of the gradient would be correlated to the diffusion rate. So the higher the concentration, the higher the dissociated ions will be. So it will have a denser electric equipotential line distribution. And second, we will see that concentration will change with time. You can know from the fixed second law, which is the concentration will be changed by time. So if the initial the dissociated ions will be like this, and go over with time, it will become more general distributed. And for second experiment, I changed different electrolyte. So in my experiment, I used copper sulfate for my strong electrolyte and acetic acid for my weak electrolyte. And here are the experiment results. And we can see that for the strong electrolyte, which is the copper sulfate, it has a higher density at the electrode. And so explaining this is because the strong electrolyte will dissociate more ions, so you have a denser electric tensor line distribution. And the third is the settling time. So we can see that if we instantly measure, which is we instantly apply the power supply, and so the water will start to dissociate ions, and we instantly measure different dots, and we map out this paper. And after 1 hour of waiting, the equipotential line will be more evenly spread out because the ions will be more evenly distributed. And another thing to mention here is that the instant measure have a higher voltage variation, and after 1 hour, it will have lower voltage variation. So just as I mentioned, like in the experiment 1, that according to the fixed second law, the concentration gradient the concentration will be affected by time, and it will be more equally distributed around the plastic board. So you will have a less dense equipotential line. So here's a conclusion. So firstly, in our experiment, we did the experiment to find out that the water depth won't affect the voltage gradient, and it won't affect the equipotential line distribution. And second, we used double layer theory and Fick's law to explain the deviation of the equipotential lines. And the reason for the non-symmetric equipotential line, firstly, we think that is a concentration change. And second, is the ions traveling with respect to time. So okay, this is the reference. Thanks for attention.
Okay, thank you, Mr. Reporter, for a wonderful presentation. First, I would like to ask, what surrounds your container of fluid?
We use a plastic board.
Okay, it's a plastic board, thank you. So, did you consider using a Poisson-Boltzmann distribution to model your theory?
Boltzmann, you mean the distribution of ions?
Never mind, we'll talk about that later. Did you consider a minimum voltage that would cause the electric double layer effect?
We didn't test it.
Okay, did you consider the repulsion forces that are on the electrode, like the electrodes, like the cathodes and the...
Can you specify the force?
The depletion of ions as the cations move to the anodes they accumulate. Did you incorporate that into your theory?
We didn't.
Okay, thank you. You mentioned that for experiment you use 2 probes. One is fixed and one is moving around. How long is the tip of your probe?
Can you say it again?
So for experiments, you have one fixed probe and the other, and you measure the voltage difference.
Yes.
So what is the length of the probe?
It is like 1 centimeter.
Okay. Did you consider the electric potential in the z direction?
We didn't consider it.
Nor equipotential line either.
Only measure in the XY plane because there is only water over there.
Okay. Did you consider redox reactions that could be occurring at the anode of the cathode?
We didn't consider.
Okay. Did you use any computer simulations to help solve your equations?
No.
So you solved impossible to solve equations by hand analytically. Okay, it's okay. Let's move on. Did you test the repulsion forces on the electrodes?
You mean the repulsive forces on the electrode?
Yeah.
We didn't test the repulsive.
The relation time.
Hello everyone, today I'll be opposing numeric potential lines. So here's the problem statement. We'll begin our structured investigation with the phenomena an explanation against a theoretical model, experimental analysis, and future works and implications of the molecules. So here are some pros and cons of this for this presentation. First is the demonstration and visualization of the setup was very clear. Some variables like concentration were tested, and he also explained the double layer effect. However, he did not consider electric boundary conditions, did not consider redox reactions that occur at the cathode and ion anodes, nor the size of the ions, nor the local charge density. He also did not consider using an already existing equation to model this phenomenon. He also did not indicate the comparison between theoretical and experimental results, and unfortunately, I didn't see any units on his axis. Nor did he clearly indicate how his theoretical his experimental value deviates or to what extent the lines are varied. Also, he did not seem to know specifically the length of the rod, which is really important, and he also did not consider the optimal measure stability factor. So our point of discussion will begin with the setup. I want to talk about the possibility of using two graphing papers as a suggestion, the length of the rod, and using the tip of the electrodes. Touching the bottom, and we'll like to talk about boundary conditions, the Poisson-Boltzmann distribution Witt-Chapman model, which have already existed for more than a century that can be used to model this, and also the electrode touching the bottom. For experiments, we would like to talk about changing the voltage threshold to get the electric double layer effect, z-direction equipotential lines, and the effect of temperature. And most importantly, we'll talk about diffusion and accumulation at the anodes and cathodes. That was our experiment. So I think we may begin our discussion. Okay. Mr. Reporter, can you again show me your phenomenal demonstration? So where you have that's Okay, so this is the top view. Unfortunately, you don't have the side view. So I must ask you, are these electrodes touching the bottom of the surface?
It is.
Okay, that is good. So did you consider, do you think equipotential lines in the z direction will happen?
You mean that there's a layer of water and there will be.
Yeah.
So I didn't have the distribution within the experiment to test it out, but I do think that there will be the equipotential line like in 3 dimensions.
Well, do you think they're going to be symmetric in the z direction?
Well, I don't think it will be symmetric.
Okay, I actually think if your cathodes and anodes are pushing the bottom like in your experiment, they should be symmetric. Because if you have a tank of water, a liquid like this, let's say this is your cathode pushing the bottom, and this is your anode that is also pushing the bottom. Whereas if you have one of them that is not touching the bottom, and the other isn't touching the bottom, what you will see from equipotential lines is that, let's say these are 1 volt, 2 volt, 3 volt equipotential lines. They actually extend below this thing. Whereas over here, when they are actually touching the bottom, they do not extend below. So they will look like this, this, this. So in your case, where your anodes and cathodes are actually touching the bottom, I do not think the z direction equipotential lines will matter. So on that point, I must respectfully disagree with you. Okay, and another point I would like to mention with you is that you said you use a passive companion. And the interesting thing is that I already predicted your answer. Because could you please go to your theoretical graphs of equipotential? So like this one or this one or this one? This one will be good. No, the one, this one. The next slide. All of this is good. So notice how you have two very different equipotential lines, theoretical graphs, right?
Yeah.
So one is, the one on the right is enclosed, while the one on the right is kind of deviating.
Yes.
First, I would like to ask you if you're aware that the electric field of a metal surface is always perpendicular to its surface. Yeah. So let's say you, let's say this is the top view of your everything, and this is metal. Okay? So that means, and you have your 2 electrodes over here. Since the electric field is parallel, you also know that the equipotential lines are parallel to the electric field. Therefore, they will be perpendicular to the field. Therefore, they will be perpendicular like this, and the effect of the electrode will make it so that all has concentric circles like this.
Also, are you proposing that we should use the metal container to help your experiment?
Yeah, I think if that is a theoretical model, and this is your experimental, I saw clearly that this was a plastic container.
Yeah, it's a plastic container.
Plastic doesn't have some mental effects that would produce that graph. So that is one suggestion I think you might be able to have, which is a valid condition. Also, you mentioned something about testing after 1 hour going on.
Yeah, is that every time? You mean the third experiment?
Yeah. So interestingly, we both explored the best time to measure in our experiments, but what we actually believe is that here, so over here you'll have the equipotential line starting forward. So the concentration versus time. Here we have a concentration versus time graph of a certain anion. So let's say you have Na plus. Then it will be something like, it will be unclear over here. But after a while it will be stable. And then it will be chaotically decreasing like this. Yeah. So did you measure in this time interval or in this time interval?
You should have measured in this time interval.
This one.
Yeah.
Oh, then we must have had extremely different experimental parameters, because I believe this time interval usually occurs around from 5 to 10 minutes. Whereas this time interval curiously was approximately 1 hour.
Okay.
So if you did use this, then good for you. But if you use this, I would like to suggest that because this time period has a lot of confounding variables, such as cations and anions reacting with the solution, forming rust and all of that, there will be confounding variables that might affect the solution. Also, you mentioned the electric double layer effect.
Yeah.
So let's say you have a graph of, it's going to be not going to be linear, it's going to be drastically increasing over here, and it's going to be a diffusion there in the middle. And then another one. This is because the ions at the end, at here, increase their own electric potential.
Yeah. Okay. Yes.
Did you consider the specific conditions for these layers to occur? These are called stern layers.
Yes, so we didn't consider in our experiment.
Oh, sorry, I thought you did consider the electrical layer effect.
Yes, we did consider it. So we use this to explain that why it will be denser at the electrodes.
So my question actually meant to be, did you explain what parameters will cause this to occur? Because not under all conditions will the stern layer occur.
So we didn't do experiments on here, but we do know that we could create an electric field and it would affect the experiment results.
Okay, so actually an interesting thing I think you might want to consider is that there's a minimum voltage required for this to occur. Okay, before this minimum voltage, you actually won't see any electrical layer. It'll actually look similar, like it's going to be a little more similar to this. Why? Because you need a threshold voltage for the redox reactions to start occurring, right? You need the electrolysis. For example, you have a solution of say NaCl in your solution.
Can you explain what is a redox?
Because here you have a positive cathode, right? And then you're going to have negative ions and here, so they're going to have redox reactions. So again, as I said, you need at least a minimum voltage for these reactions to occur.
Okay.
And without the reactions to occur, they can't really adhere to the side. So actually, you'll find more of this kind of distribution. So I think you might want to take that into consideration. Also, from what I understand from your presentation, you seem to know the length of the probe tip, but did you see the length of the probe tip as an important measurement or parameter to your experiments?
We didn't consider it in our experiment. You know that it is kind of a tip shape. Yeah, so we didn't consider the effect of it.
Okay, so a suggestion I would like to make to you is it's also a quite clever insight. So I think it would be important to take into account the length because say as we draw earlier at this thing, this is your anode, a cathode, and this is your anode. So you're going to have electric potential lines over here like this, right?
Yeah.
And you insert your probe like this. But you're going to try to make it a straight line, but you know you can't. It's very difficult to
yes,
have a very straight. And the thing is, if you have a very long probe tip, let's say the probe tip is very long.
You would like to
So this will be one. So if this is 1 volt, 2 volts. Well, if you were trying to measure like the 2 volts over here, and you make it a slight tilt, and the point length is too long, you actually get around 1.5 volts because, as we know, a probe measures that using an average sum over all of this. So, another thing you also did mention the electric double layer effect. So another thing, phenomenon that occurs over here is that first, obviously, you have a lot of anions over here. So, do you want to offer an opinion as to what the anions will do to the anions over time?
Okay, so over time, the anions will attract over here, and they will create an electric field.
Okay, so I was more specifically asking what would happen in this with regard to the cathode and the anions, like very specifically without regard to the rest.
So does it supply the same voltage over time? So are you asking me that how will the cations move?
I'm asking how will the properties of the cathode change?
Okay, so if so because we use like a carbon like electrode, so I think that it would only like dissociate water.
Okay, so an interesting thing to note is if you have something like this, they will start to adhere onto this thing. So they will actually cause some chemical changes in property. And depending on if you have some kind of chemical reaction, this plus this, these things combined, an increase in something like say this will cause the reaction.
Okay, so
that's an important insight.
Okay, so you're asking that the chemical reactions at the electrode.
Yeah, the reaction. Also, this should be a short point. Have you heard of the Poisson-Boltzmann distribution or the Gorey-Chapman model? Because that came out in around the 1800s that described both electrical effects and general potential.
I've heard of it before, but I didn't know the very detail of it.
Okay, so that's another thing I would like to consider you to use in the future. So this was about the accumulation of anions on the cathode. And on the anion, you're actually going to see, depending on if this is a gas or a liquid, there could be gaseous bubbles that emit from that part, and that will also cause a shift left, so that is actually called accretion. Do you think temperature will play an important effect?
Yes, listen to appendix.
Can opponent summarize the discussion?
Okay, so the reporter and I had a very fruitful discussion. First, we discussed boundary conditions, which the reporter agreed with me that they would change the overall shape of equipotential lines quite drastically. We also discussed the optimum phase of measurements, which interestingly, we thought the same time period would be around 5 to 15 minutes and 1 hour respectively. And the reporter also kind of agreed with me on that point. We talked about accumulation and depletion on the cathodes and the anodes, and we talked about how that may affect certain chemical reactions that will affect the concentration and the properties of it. We also discussed how the length of the probe tip could alter the change in voltage that is measured, which may be a cause of large errors. We also talked about how if you have cathodes and anodes that touch the bottom of the surface, the z direction equipotential lines won't matter because they will be symmetric.
Review and explain.
Okay, first, to clarify. Sorry. Could you explain how the equipotential line changes over time?
Okay, so this can be explained by the Fick's law. So
I mean, how it changes over time.
change over time.
Yes,
So
how it changes.
we didn't do the experiment result, but I can explain to you because at first we give it the power, so it will start to dissociate.
Yeah.
So dissociate of ions and moving across the water could be explained by Fick's theory. Could be explained by Fick's theory. So
I'm not going to be explanation, I mean, how it changes over time.
yeah, so first it will be more density and the electron, and it will become more equally distributed.
Okay, I've considered electrolysis in your experiment. Have you considered any electrolysis?
So we use iron rod. So I think we use iron rod. So we use like copper rod. So that we didn't consider.
Okay, just to extend on this point, have you tried other materials that iron that will maybe dissolve in the water?
Yeah, we did because it will start to like more using water.
What effect do you think will have if we try those materials?
Just as the opponent said that we could test it in the same like the time where the electric potential is like more stable, so we could test it in that time. Maybe we get a more accurate result. It has like we use other materials.
For the opponent, you mentioned the Z direction of the equipotential line. Can you explain why it is significant?
Because when the cathodes and the anodes touch the bottom of the surface, they will be symmetric with respect to each other. Whereas if they're not, they will extend below the cathodes and the anodes.
Okay. Also, do you think when we apply a voltage, what will we measure? What will we measure? If we apply a voltage that is shielded by the EDL, will it be constant or will it be zero voltage?
Excuse me, could you define what you mean by WL?
Electric double.
So could you, if you apply a voltage that is
Yeah. Do you think we will measure a constant voltage or zero voltage if we apply the voltage that is shielded by the EDL? Electric double layer.
I think that I don't understand what you mean by
so
shielded
it's a-
because the
yeah.
voltage will increase drastically at the EDL, at the certain layers of the EDL, if that's what you are referring to.
No. Okay. For your experimentation, you have nuclear probes, right? Backhand.
Yeah, we use 10.
And you mentioned the effect of the electric layer, double layer.
Yes.
Do you think your motion of your hand might like disrupt the layer?
We think the double layer happens on the electrode, so the voltmeter, the probe does not.
Okay. Thank you.
Okay, thank you, Bob. Deliberation time.
reviewer of the numerical, I'm going to be reviewing problem number 8, the coefficient y. This is a problem statement, and we think the key points will be the deviation between expectation and theory, and the explanation theory. For the reporter's performance, he demonstrated phenomenon, and he said the results differ from the expectation. For the theory, they explained the double layer effect, and also Fisch's law. Also for their experimentation, they experimented with different concentration, different electrolytes, and different settling time. Their strengths include clear demonstration of phenomenon, they gave intuitive explanation, and they had good time control. However, they did not consider limitations of the theory. They had no units in some of the graphs. They had false units in their equation. They had not fully explained the effect of EDL, which is electric double layer. And also, they had faulty measuring methods, which might disrupt the ion in their water. For their opponent, he did a good summarization of the reported presentation. He pointed out many points, including boundary conditions, chemical reactions, and different electric potentials along the Z direction. For their cons, they spent too much time on experimental detail that could be seen in the photo in their presentation. For the discussion, the opponent first asked, does the equipotential line in the Z direction matter? The reporter said they are not sure about the effect. The reviewer agreed with the opponent about the shape of the equipotential line in the Z direction, but we do not see how it is significant in the shallow tank. Next, the opponent asked what's settling time measured. And then the reporter said, we measured the stable part of the voltage. The reviewer agreed with the opponent that the reporter is not measuring the state of the stable voltage. Okay. Then they discussed about the effect of EDL. The reporter said that they used EDL to explain the voltage changes at the electrode. The reviewer thinks the opponent is correct about the threshold voltage because EDL may shield the applied voltage. Next, they discussed the orientation of the voltage. The reporter said they didn't consider this since they had a little, they did only a little bit of their probe inside the water. And the reviewer thinks that the experiment can be better controlled. And next, they discussed the properties of cathode and how would it change with respect to the cathode. The reporter said they only use graphite cathode, so there will only be electrolysis of water. The reviewer said electrolysis of water will change the EDL and the properties of electrode. For the point this, they missed the effect of electrolysis on the measured voltage. Also, they missed the relevant parameters such as electrode shape and the material. Also, they missed a discussion on how EDL develops with respect to time. And also, they didn't consider the effect of temperature. They didn't measure the amount of ions in the solution, and they did not talk about the effect of probe material on the ion distribution and the equipotential line. Also, they do not think that the motion in their experiment would affect the ion distribution and the double layer. However, the reviewer thinks that it actually affects the phenomenon. Thank you.
Okay, the order concludes the remark.
Okay, so for the concluding remark of this question, first we think that the Z-dimensional potential lines will be matter when we don't attach an electrode down into the water, but we didn't have done the experiment for it, and maybe we'll do this in our future work. And also we talk about the effect of the temperature can be derived from a formula, and that as the higher the temperature it is, the higher kinetic energy of ions there will be, and it will cause a more unstable situation. And third, the ions move to the electrode as time passes and causes a main deviation for the lines. And we also measure the equipotential lines instantly while we do an experiment, and we agree that we should measure in the time where there is a more stable voltage, so we can minimize the deviation of the equipotential lines. And furthermore, we use copper. We use copper as our electrode, so we didn't consider the effect of the electrolysis. Okay, thank you.
Okay.
just a question for Trill. The answer is just yes or no. Is the phenomenon here time dependent or time independent? Just yes or no.
Yes, I think yes.
Yes.
I think yes. Since the ion are just like accumulating.
Measurement.
Sorry?
Measurement of the phenomenon.
You mean the definition like yes?
So time dependent.
Yes.
It is time dependent.
Yeah, I agree with that. For the reporter, you mentioned some J. Is it the electric current or what? If you mention some quantity J in your presentation,
So the J is the
is it the
diffusion rate.
electric current?
No, it's the diffusion rate.
Diffusion
The
rate.
diffusion rate of the ions. The diffusion of the ions, yes. If you mean the Fick's law, so Fick's law. So the J here is the diffusion rate. Sorry, I didn't explain in my report. So
The gradient time, there is a gradient time,
yeah, J is the diffusion flux. So here it means how the ions that would diffuse into the water, and we could use a Fick's law to explain that the concentration would there will be a concentration gradient across the
And did you measure if there are any electric current between the two electrodes?
No, we didn't measure
You
it.
didn't? Do you think there will be some electric current?
Between two electrodes.
Yeah.
Yeah,
you
we
didn't.
didn't think so.
Okay. What about the opponent?
There will be
And,
electric current, yes, between the electrons.
and will it have certain effects on this phenomenon?
Yeah, maybe like the variation in the current maybe will affect the electropotential.
Okay.
Yes, I think the current will come in effect because it may cause the ions to move around.
Any question? I have one question for you guys. If you set your experiment, you just maintain 1 day. What happens? Maintain 1 day and 24 hours. What happens for your experiment?
If you do your experiment for 1 day,
So I'll draw a diagram. So here is your cathode. There's actually going to be some, or let's say this is cathode to make it clear. So let's say for the solution used is like zinc sulfate. So now you're going to have some zinc ions that accumulate onto this thing, metals that accumulate onto this thing, and they will cause their own electric field, which will make the electric field even more random.
I think if you apply like enough voltage, you will still be able to like measure your equipotential light, but if you have like insufficient voltage, then you won't be because of the double layer effect, you wouldn't be able to measure.
Okay.
So you mean that across the time?
Yes.
So we think that actually across the time more like 1 day, the concentration distribution will be evenly distributed, so we will have a more like distributed equipotential lines.
Okay. Unknown is the score time. Please show score. For the reporter 8, 5, 8, 6, 7. Okay, for the opponent, 9, 6, 8, 7, 8. For the reviewer, 8, 7, 9, 8, 8. Very easy. Okay, we ended this section. 10 minutes break.